So let's get on to the next part of our program. Also from UNC-G Physics and Astronomy Department, we have Anatoly Miroshnichenko, who is is familiar to us because he is every year he gives a presentation at the technical meeting of North Carolina astronomers. But he's never been to TriStar, and he's been here at UNC-G since 2005. And interestingly enough, just last month, unrelated, going through some papers in my office, I found the notes I took at the colloquium he gave when he visited UNC-G for his job interview. And Steve Danford again invited me over to come and see our candidate. And David Herrick and I went to that talk. David's back there, and he it looks like the title was Dust Formation Near Hot Stars. But David, I think, remembers one particular type of star that you mentioned frequently in that talk. B-E stars. So, and Anatoly still talks about those, I think. And so if you want to see the historical relic, I will have it. It's in my files of talks that I went to. But like I say, Anatoly's been at UNC-G for nearly 20 years now. He's the director of the three-college observatory there, and he has really brought that observatory sort of into a new era in his years there, and he's doing a lot of interesting work there. And today he'll tell you a little bit about that, but he's also going to talk about how amateurs are part of a sort of a new revolution in spectroscopy. So I'll turn things over to Anatoly and let him tell his talk.
Thank you. Okay, so let me get this set up. Okay. All right, so can you hear me? Well, for a microphone. Well, it's really hard to give a talk on a very different topic after Alicia's presentation about the success of our astronomy program at UNC-G and that hardship we are going through now. So if you look at kind of my titles, you can figure out that I'm a professor of an eliminated department and director of an observatory, which the administration of our college, of our university probably doesn't know. Anyway, so we did quite a good job with Free College Observatory. It was actually designed by our older generation person. People already talked about him, Professor Emeritus Steve Danford, who came to UNC-G in 1976 and designing the Free College Observatory, which is a collaboration between UNC-G, North Carolina A&T, and Guilford College, was one of his first projects. Then the observatory was open in the beginning of 80s, but until about 2011, it was rarely used for science because of its not very fortunate location, low elevation, thick atmosphere. But with the advent of new technology, we were able to use it in a new way with spectroscopy. Alicia highlighted quite a number of projects she did with students. Steve Danford was also working always with students, and me too. Recently, because of our basically achievements in spectroscopy at the Free College Observatory, we were able to publish several papers, almost solely based on the results we take here, and some of our students participated. One of them is here, Holly Burrs. Sorry, my pronunciation. She has been working with me for several semesters, and she is now studying one of the Brickety stars, which is a pretty bright one, almost naked eye star, but there are still lots of puzzles around. I'm going to talk about amateurs and its contribution to the science of astronomy. various projects which were done in the past and now. And the reason for that was that Tom told me that there will be quite a number of amateur astronomers around here at this convention. I've been collaborating with astronomy amateurs who actually know so much that they can be considered professionals for about 20 years. And here is sort of topics which I'm going to talk about. First, we'll define an astronomy amateur according to Wikipedia. Then I will give you some historical examples of really great discoveries amateurs by definition did over the centuries. And the last two topics are going to be, let me see, kind of longer. I will talk about several groups of amateurs, mostly in Europe, who actually they have some very active people there, but they collaborate with the entire world, including professionals, and also give you some examples of this collaboration. So pro-am, professional amateur collaborations, this kind of acronym became very well known. Okay. So let's go to definitions. Wikipedia says that amateur astronomy is a hobby. That's pretty fair, where participants enjoy observing or imaging celestial objects in the sky. That's, I think, not very literal because celestial is already sky, translated from Latin. So we need to correct here. And they are using some kind of either naked eye or little aid. And then they go on, that definition, the description of amateur astronomers saying that they don't use field astronomy as the primary source of income or support, and usually have no professional degree. Yeah, that's true. There are not many astronomers in the world anyway, and there are some who actually get doctorates in astronomy or astrophysics, but then they don't work in the science. And one of the good examples would be the leader of the rock band Queen, Brian May, who earned his PhD in astrophysics in 1968, but he was already playing guitar at the time, and his career was totally in music. But amusingly, I heard his talk on a Star Muse Festival, which celebrated 50th year of the first human space flight by Yuri Gagarin in 2011. And Brian May was talking about the dangers we can bring to space if we have wars and other bad things on Earth. So this picture shows an amateur taking some notes while observing the sun. So I think it's not a very instructive picture because Galileo would observe the sun like this with some smoked lenses. Nowadays, both professionals and amateurs typically project the image of the sun on the screen and study the sunspots or whatever activities, some of them at least showed by looking at the screen. So anyway, so we defined the amateurs in astronomy, and now I go ahead and give you some examples. Probably we cannot distinguish between scientists and amateurs in the ancient history. We don't really know what Archimedes or Eratosthenes did for living. Well, at least I don't know. Let's start with some kind of closer example. So who knows who that person is? He's not typically in the Western textbooks. So he lived in the city of Samarkand, a beautiful city with many temples and pretty nice architecture. So it's now located in the modern country of Uzbekistan. So 14th, 15th century, he built this instrument, which is still there. So this is a quadrant. So you can see that it's a quarter of a circle. Here is a window, and depending on the height of the star, you can observe its altitude angle. Then if you record time, then you know its position relative to the sun, and you can determine coordinates of a star or a planet. He did a catalog of over 1,000 stars, and it's a very valuable contribution, because before him, Claudius Ptolemy in the 2nd century AD did the same, so we can compare positions of stars over the centuries, and this can give us a hint about the change of the orientation of the Earth rotational axis and our understanding of spherical geometry. Stars move. He did not need to be astronomer for a living. He was a king. He was a grandson of the Asian conqueror Tamerlane, and he got to power at an age of 14. For several years, his father was reigning, but then he resigned, and Ulugh was in charge for about 40 years. But unfortunately, all this things like our APR got into play, and his sons rebelled and killed him eventually. But that's a good amateur contribution. Now, next thing. This one. You probably know William Herschel, and many may think that he was an astronomer all his life, but in the first part of his life, he was a musician. His father was an oboist, and when he was very young, in the 20s, he played oboe in his father's band. Then he became a musical director. He actually wrote about 24 symphonies, many other musical pieces, and he started doing astronomy while he was still a musician, built a large telescope in 1770s, observed certain objects, but he became famous because in March 1781 he discovered Uranus. And later that year he switched to professional astronomy, built a very big telescope, which is larger than the Free College Observatory telescope, but it's 18th century. Anyway, that's another amateur. Now, fast forward to our days. You know that back in the 90s, there were two bright comets in the sky, naked eye comets, very bright if viewed through a telescope. One of them was discovered in the United States by these two people. Hale had actually a PhD in astronomy, but didn't work as an astronomer. And then turned out that it's a comet on a very eccentric orbit with an orbital period of about 24 centuries, so it will come back in the very distant future. That was real good. When they attracted the attention of professional astronomers to that comet, then professionals started to observe it with large telescopes, and now we know it very well. What else? Now, I'm coming to the 21st century, actually to the end of the 20th century. At that time, photographic plates, which Tom worked the Free College Observatory in the very beginning, were phasing out. The electronic detectors, which now we all have in our cell phones, were only under development back in the probably 70s. One of the first papers in astronomy with the use of these detectors, which are called charged coupled devices, or CCDs, appeared in the early 80s. With time, technology was progressing, and the cost of these devices went down. Actually, Free College Observatory acquired one of those back in the end of 1980s, but it was very expensive. So there were some photometry projects done at our observatory, but no many. So some people started to apply new devices to not only to taking pictures. So we know that many amateurs like taking pictures of various objects in the sky, but this particular person, French engineer Christian Bouil, started to actually involve people into spectroscopy. So he developed almost every spectrograph since the end of 1990s, which range from some simple devices, low resolution spectrographs. So you can detect some spectral lines, but you cannot measure their exact positions in order to figure out whether there are any changes in the positions. And his kind of highest resolution spectrograph is called V-Iris. That's its prototype on a bench. And we usually measure spectral resolving power by this ratio. So it's the wavelength of light divided by the smallest beam you can resolve in the spectrum. So for the naked eye, probably resolving power is of the order of 50, something like that. Low resolution spectroscopy goes to about maybe 1,000 or maybe even 5,000 of that ratio. And high resolution spectra can have a higher resolving power. The highest resolving power instrument I heard of has this ratio of I think close to 1 million. So you can see the spectrum with very many details, but unfortunately when you process that light into a spectrum, then the larger the resolution, the smaller amount of light go into every beam, and you limit it, even with all those large telescopes which you have on Earth now, to only very bright stars. So this is a pretty good resolution on the higher side. We use at our observatory a spectrograph which has a resolution about 3 times less. Okay, so let me get to his site. I opened already my links in order not to just answer those questions, security questions. So they're here. So that's Christian's website. He started back in the late 90s, and he was about the only one with a little circle of friends taking spectra, and he was working on everything, on cool stars, on hot stars, on the sun. So if you browse through this pictures, you can see even a radioelastic curve of an exoplanet. It's actually the changes of the radial velocity of the lines of a star, which has a relatively massive exoplanet there. So 51 Pegasi b is the first stellar system where an extrasolar planet was discovered, and the velocity scale is very fine. It's in meters per second. It means that the gravitational tug from the planet onto the star, which is much more massive, is very small, and you need high resolution and relatively large telescopes. But now amateurs can manage that with their range of telescopes, which is typically between say 10 inches to maybe 20, 30 inches. So that's Christian. And he also made many people from the amateur community to study B stars. B stars, I will have a few slides explaining what they are. So this is a database of spectra of mostly B stars, which are emission line stars of the spectral type B. This is where amateurs put all their observations. Now I think it's over 100,000 or even maybe 500,000 spectra there. And if you just click on one of those links, you can, for example, choose a star. Like, let me do HR 2845. Then you click submit. It resolves the coordinates by the name, and here you see just a sample of those spectra. There's so many of them, I think. So in total, it's about 250,000 spectra in this database, but for this particular star, which is third magnitude, I will get back to it because we also observed it a lot. There are many results from amateurs, and you can see different sites, different names, the observing dates, and you can actually display a spectrum. So they mostly focused on the H-alpha line, the strongest hydrogen line in the spectra of all the stars, but there are some spectra which cover a wider spectral range. Okay, so now let's go back. So Christian united European communities. He's in France. Oh, by the way, I want to mention that in his web page, many sub-pages are written in French. So he speaks little English, understands, of course, English, but it was hard to speak to him. We always needed a translator when we communicated. Now, he inspired this man as well, Francois Cachard, who started a company in 2006 called Chelyabinsk Instruments. And Chelyabinsk is the second brightest star in the constellation Lyra. It's a interacting binary system, and that's why, so because it's interacting now, there are many changes in the spectrum, and that's what attracts quite a number of amateurs there. So they started company, two of them. Olivier Tizy is also an amateur, so I met him in 2010. And in 2011, we were able to purchase one of those spectrographs which they manufacture called eShell. And this is what an eShell spectrograph is doing. So when light goes through the diffraction grating, it is split into one big spectrum. But in order to record that big spectrum, you need a large detector. And the larger the detector, the more expensive it is. So a solution was found to actually run that long spectrum through another dispersing device, which cuts little parts of that big spectrum and arranges those cuts on top of one another. So we have kind of many lines, each of which is a spectral range. And when we do that this way, we don't need very big detectors. That's what we get in our Free College Observatory. We lose some light because of all these reflections, scattering, but still it's a pretty efficient technique. And I have a web page of this, no, I always do it here. So I have a web page of this company. They recently manufactured a really high resolution spectrograph, but unfortunately it costs like 80,000 euros. The shell is about 10,000. So pretty affordable, and quite a number of amateurs, especially those who are more or less wealthy or retired, they can actually allow themselves to get that. So everything is here. They do accessories, they do even data reduction programs. They recently came up with a software which is called Demetra. Francois, of course, he's French, calls it Demetra. And it's a Windows-based data reduction software which allows to process spectra automatically. And you just finish taking a spectrum and it can be processed right away within a few seconds. So that's Chelyabinsk. Now let me get back. Germany. We met with Ernst Pohlmann in 2002. He probably read one of our papers, and since then we have been collaborating. So he unites German amateurs, but they work together with Christian Buell, and as one of those collaboration projects is RS Group, which is amateur ring of access to spectroscopy. They have their own website, and they store their data over there. They mostly study B stars, but some objects as well, nova stars, explosions in binary systems, then some peculiar stars like P Cygni, which is one of the most massive stars in the galaxy, which experienced a major outburst detected in the year 1600. It was much brighter than now. Now it's barely naked eye star. but it shows always the changes in the spectra, and that's what attracts the amateurs. Here I just show you some kind of not results, but another binary system which they study. It's called Vivi Cephei. It contains a supergiant, which is similar to Betelgeuse, that star in the shoulder of Orion the Hunter. And this I found on the internet. That's a sketch of the Vivi Cephei system. So it has a hot giant on the orbit. The orbit is very eccentric. The orbital period is about 20 years, and every 20 years the giant is eclipsed by the supergiant. As a result, you can see big changes in the brightness. So the brightness goes down by about 1 magnitude, and the spectrum changes also dramatically. And here is a link to Ernst and a Canadian astronomer paper about a spectroscopic study of this system. There is a little village in Austria called Honsberg. There is an astronomical community there, pretty active, so they were bugging the administration, the municipality, to help them build an observatory. And the administration promised and promised and promised, did nothing. And all of a sudden, a rich man came and gave them about €1 million, I believe, euros, and they were able to build a very nice conference center and a 1-meter telescope. It's an Austrian-made telescope. Now they have 2 telescopes. And the leader of the community, software engineer Manfred Schwartz, started biannual meetings between professionals and the amateurs. One friend of mine suggested him to invite me, and since that time I'm a speaker at these conventions, and I'm going to go there in 2 months from now. It's going to be a third such a convention. Let me show you. No, that's the paper. Yeah. So this is a picture of the participants in 2022, 2019. You always see that quite a number of people here look on the older side. So some they are retired, and they do astronomy still for hobby, and they still enjoy it. Here, there is. If you click location, then it shows you the view of their surroundings in the conference. That's a pretty dark place. The altitude is about 1,000 meters above the sea level. It's in the mountain region of Austria, near the Mozart city of Salzburg. Okay, now let's go back. Here we go. Oops, something got in. No, it gets me to the Free College Observatory. I talked about it in conjunction with 10 years of operations with spectroscopy in 2021, but it was a pandemic year. I believe it was online. So a little bit about Free College Observatory. So it's located in the middle of nowhere. It's actually in Alamance County, about 5 to 8 miles down south from the township of Graham. A few miles north from a village of Snow Camp. So the ACL latitude, it's pretty southern, which allows us to observe the entire northern sky and a big portion of the southern sky to about declinations of minus 40 degrees. We have one of the 2 largest telescopes in North Carolina and one of the 3 largest on the entire East Coast. There is one in Virginia, 1-meter telescope at Charlottesville, but I'm not aware of the recent results. And we have that Shell spectrograph, which we got in 2011, our resolving power, and it's a pretty big range of wavelengths. We can see lines, spectral lines from about ultraviolet to almost infrared. Okay. Yeah, so here is a recent view of the telescope. Until 2015, it was operated on a very old IBM PC 486 computer until 2015. Yeah. Then we got in touch with a company called Sidereal Technology, and their main astronomer, basically they do some equipment for sea vessels, but they also do that for astronomy. Daniel Gray, he came there and changed navigation system to a modern computer with electronics. So here you see one of those axes, and there is a very fine metal tape which is covered with little tick marks, and here you may see an instrument, a encoder, which reads the tick marks, converts it into coordinates, and the telescope goes to whatever location you want. Here is some images from surveillance cameras and from the screen. So we have now two PCs, Windows 10. This is the spectrum. This is the image of the star, which you observe, and so that image is produced by a little TV camera, which is right on telescope, and optical fibers transmit light to the detector, which is sitting in a wine cooler on the first floor, on the ground floor of the observatory. Everything since 2019, again with the help of Sidereal Technology and Daniel Gray, is automated. I observed that it's from Europe, from Asia. You can do it from wherever you want, provided you have internet connection. Now we have more cameras which show us what is going on around the building of the observatory. So this is what the spectrograph looks like. This is optical fiber coming from here, from the telescope. This is a unit of comparison lamps, and this is a unit which rides on the telescope, and it has one end of the optical fiber, and this is the opposite end. Since we started doing observations, we accumulated over 10,000 spectra. We observed for more than 1,200 nights. Before automation, we would need to come there in person, and the weather over there in Greensboro can be very different. So sometimes you just come out and see clouds and you don't go there, but it can be completely clear. So before automation, we would observe on about 80 to 85 nights a year. Since we automated it, it happened in 2020. 2019 was the process of automation done, but the real observation started in April 2020. We now can observe every other night. And last year, we observed on 168 nights from there. But the location is very good because the atmosphere is thick. It does not actually block too much light, but it blocks all the cosmic rays. When you take a spectrum from a high altitude, then you are limited on the exposure time because those cosmic rays hit the detector multiple times, and you need to clean your results. And in our case, we can observe even up to about 40 minutes and still have a very few cosmic rays on the image. Here's some about local collaborations. For 3 years, we collaborated with retired healthcare specialist Peter Prendergast, who bought a 50-centimeter telescope and the same spectrograph, a shell spectrograph, and put it close to Pilot Mountain. Then he moved it elsewhere. And for 3 years, he took over 500 spectra of 35 stars, and we added those to our database, and he's a co-author of some of our publications. Then he decided to do some astrophotography business and sold that spectrograph. So we stopped collaborating. There are some other collaborations with the United States amateurs, just recent ones. Karl Savitsky observed Beta Canis Minoris for us, and Gerald Persha did B Perseus, which is a triple system. We have some 200 spectra of it over the course of about 7 years. Just need to summarize and figure out how that third companion, which is a low mass star, affects the motion of the internal binary in the middle of that system. So there are many interesting projects here. So why B stars matter, why many amateurs are attracted to it. So B stars, or actually it's called the B phenomenon. It's appearance of emission lines in the spectra of stars spectral type B. This is the range of photospheric temperatures. They typically rotate very fast, which may be a result of formation of a star. So it just formed out of a fast rotating cloud, or it may be induced due to mass transfer in a closed binary system. So when one star, the more massive star in the system, evolves past the main sequence, the hydrogen burning stage, it gets larger, and it can reach the boundaries of the region of its gravitational dominance, which is called the Roche lobe. And when it reaches this point, the inner Lagrangian point, the gravity from this star and from this star are equal. So if you push particles a little bit, they can actually start pouring on this companion. As a result, quite a lot of material can be transferred from this initially more massive companion to initial less massive companion. A disk can form, and this disk gives rise to the emission lines. Essentially, the material in the disk absorbs some ultraviolet radiation coming from the stellar atmosphere, and it ionizes gas there. Electrons fly free, but then they're captured by other atoms of hydrogen or other elements, typical hydrogen because it's the most abundant element, and produce spectral lines and some continuum radiation. And the profiles of these lines depend on the tilt of the disk with respect to the line of sight. That split is due to the Doppler effect because part of the disk moves towards us, and it produces this short wavelength component. The opposite part of the disk moves revolves around the star away from us, and it produces the second redshifted or long wavelength component. And then depending on the tilts, we either observe much of the surface of the disk or small part of the surface, and it plays a role in the intensity and the central depression. That central depression is produced by a region which is in front of the star, maybe a little bit behind the star, but its area is not that large, and that's why the amount of radiation is smaller than in the peak. So it's not absorption, it's just lack of emission. For about a century, the first model was introduced by Otto Struve in 1931, pretty famous American astronomer, whose great-grandfather was founder of one of the oldest Russian observatories, where I started my career, in fact. We don't know why those stars rotate fast. I just gave you two different reasons. But theoretically, it was shown that only fast rotation is not enough. And recent discoveries, especially observations from space, show that the brightness of those stars, they fluctuate. It means that there are some pulsations showing here. So those red regions, they go away from us. Some parts of the surface, these regions go towards us. This kind of non-radial pulsations, which allow more particles to be expelled from the surface of the star. There are many such stars in our galaxy, about 200 brighter than 7 magnitude, and they can be easily reached with small telescopes. So the B star community works on the stars a lot. And here are a few our projects with amateurs. One of them is one of the brightest stars in the actually pattern, that constellation of Scorpius, called Chuba, old Arabic name, or Delta Scorpio. It was discovered to be a binary by lunar occultation in the beginning of the 20th century, but then it didn't show any traces, any phenomena of changing brightness, and it was treated as a standard of spectral classification. So B0 type stars, so B04 means that it's a little bit above the main sequence. Then when interferometry or very high resolution technique became available, the secondary companion was resolved, turned out to be also a B-type star, but we are still unsure what the temperature of the surface is. It was bright, it was fainter by about a factor of 4. The orbit was determined, but not with very high confidence. The separation between the companions go between 6 and 200 milliarc seconds. So you cannot detect, you cannot resolve this pair with any other technique. So 200 milliarc seconds is 2/10 of a second of arc. And orbital period is very large. Typical orbital periods of these stars are between weeks and maybe 1 year or 2 years or so. So it was a second magnitude star, but an amateur from Argentina who observed this star with the naked eye, Sebastian Otero, detected a 3% increase in brightness in the year 2000. He published a little telegram about that, and then some professionals took a spectrum, and they found that there are emission lines getting developed. So that star started the primary component, the more massive component, the brighter component, started developing a disk around it. And this light curve, so you see 2.2 minimum, and here is about 1.6, which is a ratio of 1.7, 70% brighter. The disk, which is fed on ultraviolet from the star, becomes visible radiation, and it adds 70% to the brightness of the star. This was all done by amateurs with some telescopes and with a naked eye. At that time, I worked at the University of Toledo. We found that interesting to observe that star, and these are our measurements of the position of the H-alpha line. It turned out that so when stars get close to one another, they start moving faster around the center of mass, and that's why the velocity, the basically position of the H-alpha line or any line changes. And this peak gives us an idea of the periastron passage, the closest approach between the two stars, and the shape of this change of the radial velocity give us a clue about the other parameters of the orbit, like eccentricity and so on. And these lines are actually predictions from interferometry, which were significantly off for almost every parameter of the system, of the orbit. So because the orbital period is about 10.8, close to 11 years, and amateurs got excited with our results. By the way, even professionals since that time call me a Mr. Delta Scope, because I've been publishing about one paper in a few years about new observations of this star. So they convinced me to write a proposal, so the amateurs, for time at this telescope. It's 80 centimeter telescope, Observatory Del Teide. The volcano Del Teide is here. It's located on the island of Tenerife, and we got 10 nights, 10 observing nights. These amateurs, Thierry Garel from France and José Ribeiro and Armando Fernanda from Portugal, they came there to actually do some joint project. Garel, by the way, is a French dentist. He's pretty busy at his clinic. Fernanda was the head of air controllers working for the entire state of Portugal, but he retired and then kept enjoying the amateur astronomy. So we would observe for about 6-8 hours at night, then had a 3 to 4 hour sleep, then jumped in the car and go to the beach. It was very, very enjoyable experience. And in about a year from that time, we published a paper with about 20 amateurs. And these are just some changes in the profile of the H-alpha line. The next periastron was in 2022. And that time, we already had our spectrograph at the Free College Observatories. We collected over 100 spectra, and we are close to actually publishing it. Because of this APR thing, I just got slowed down. Anyway, so from the position, the central position of the H-alpha line and some other lines, you can constrain the orbit. You see some features. When the two stars get very close, the secondary companion, the fainter star, actually goes through the disk of the primary star, disturbs it. So all kinds of interesting events can be studied by observing that. Then this is a star which you can see here. It's part of the constellation of Aquarius, one of those zodiacal constellations. It's located to the south of Pegasus and close to the brightest and second brightest star in Aquarius, Alpha and Beta. It was a very active B star with a strong H-alpha line profile back in 1980s, and you see that that profile looked like just one peak. But then something happened in the year 1989, and it started losing that brightness of the entire system in the amount of light it emits. And also the strength of the line and the profile changed from single peak to double peak. And now I think there was actually this is a free peak profile, and this double peak feature is simply masked or veiled by some central peak, which may be due to the transfer of material between the two stars in the system. By the middle 1990s, the star completely lost its circumstellar material, its disk, and acted as a normal star. And that allowed us to determine the period of changes in the positions of spectral lines and basically conclude that it's a double star, it's a binary system. So for about maybe 5-6 years, there was no disk around that. Since the beginning of 2000s, the material started flying away from the main star, and this profile of the H-alpha line appeared again. Amateurs were following this star, and finally they approached us, professionals, in order to help interpreting what is going on. So what we were doing, we were measuring the ratio of the intensities of these two peaks in the spectrum. And it turns out that that ratio follows the orbital period, 84 days, about 3 months. And then using these profiles, running them through a hydrodynamic code, we were able to restore the density structure of the disk. So this is the main star in the system, this is the secondary companion, and it turns out that there is some kind of a blob of material which moves in sync with the secondary companion. So it was one of the first results on observational results on this kind of process. There are some theoretical expectations, but looks like the reality is different. And now this star actually gets back to this profile, so the amount of material in the disk still increases, and we observe just the next cycle of activity. Then another interesting result we got from Beta Canis Minoris, and this is the second brightest star in the little helper of Orion the Hunter. That's the small dog. You all know Sirius, the brightest star in the sky, but it's in the big dog. It's a third magnitude star, easily recognizable if there are no significant light pollution, of course. And we observed it for about 20 years, since 2011 at the Free College Observatory, accumulated like 300 or more spectra. And for each of the spectrum, we measured this ratio, this intensity over this intensity. And here in this sample, one profile has a short wavelength peak stronger, and the lower profile has the long wavelength peak stronger. When we analyze that with Fourier analysis, we have this sinusoidal pattern, although it's pretty noisy, but we did that several times in different years, and we always getting the period about half a year, which is a little bit suspicious because it's half the Earth's year. On the other hand, we are able to observe the star not only for half a year, we can observe it for about 9 months. And that suspicion that it's due to motion of the Earth is eliminated. So many amateur spectra went into this graph. And one of those reports on these results published in the end of last year in an emerging popular scientific journal called Galaxies. So there, before that, there were about 5 highest rated journals, research journals in astronomy, Astrophysical Journal, the Astronomical Journal, then one European journal, Astronomy and Astrophysics, British monthly notices of the Royal Astronomical Society, and one from the Astronomical Society of the Pacific. But now there are more journals, professionals at least seem to read it, and that's why we decided to go for publication in that one. So there are a number of results we got from the Free College Observatory. Almost in all these projects, our students were involved, and sometimes they're not even physics students. One of them, Duncan Lauder, was a Spanish major. He took my class, which was at that time online in 2021, but he wanted to do some project in astrophysics. Another student of mine helped him to install the software for data reduction and analysis, and we did a project on the second companion in the Mizar system, the middle star in the Big Dipper, and we constrained the orbit. We made it more higher quality. So there is quite a number of these results. And now let me show you something strange. So what is that? Some Cyrillic symbols, some Greek letters, some numbers. You know, I'm of Russian origin, so I can translate it for you. This is a constellation, then Taurus, Gemini, Aquila, Perseus, Draco, and so on. These Greek letters, of course, the Greek letter assigned to that particular star. This is right ascension, this is declination, magnitude, distance. Only a few distances were known at that time, and absolute magnitude or measure of luminosity. This is one of my notebooks, which I assembled in 1974. 50 years ago, I was amateur, and I built my own telescope from some condensed paper and lenses off shelf. It gave very terrible images, but it was so exciting. And now that UNCG administration is going to take my pleasure from me, it will never happen. We will stay for our department, for our university, and we hope you can help us with your support. Now, conclusions for amateurs. So yeah, you saw that even in the past, many centuries ago, they contributed to the science of astronomy a lot. By the way, we can consider such astronomers as Tycho, Johannes Kepler, to be amateurs because they were astrologers. That's what they were made a living on. Then many important discoveries they did. They discovered not only planets, comets, asteroids, they discovered some interacting galaxies. So stargazing with a telescope, especially taking pictures, can be very fruitful. In the 21st century, attention maybe shifted a little bit, but not, of course, everywhere. People continue to take very nice pictures there, but spectroscopy became affordable, and with spectroscopy we advance quite a number of directions in astronomy. And now amateurs, large groups, not only in Europe, but there's quite a number in the United States. They work with professional astronomers. There were at least 3 professional amateur symposia in Germany. Then the third one is going to occur this May in Austria. And there are some people who do spectroscopy in the UK, in Australia, in South America, and we all join forces. So consider maybe joining that community. But I believe that you just keep enjoying your work as amateurs, and that's wonderful. Thank you. Time for a couple of questions. Yeah.
So the amateur astronomy may be a dying field. Will they ever, amateurs collaborations ever get an opportunity?
Well, you just probably need to apply for time, and it's better to get done with professionals, just again, form teams. There is a big variety of space telescopes now. It's hard to get on because it's limited, but I think it's not possible.
All right. Thanks
Thank
again,
you.
Anatoly.